Hey viewer, welcome to Safi Next with the third part on the phenomena of Compton effect. In this video, I will discuss the impact of Compton effect on quantum theory and also few of its applications. So first, I would like to begin by making its comparison with photoelectric effect. The photoelectric effect reveals only the particle nature of radiation or photon through the equation E equals h nu. On the other hand, in addition to the particle nature, the Compton effect also proves that photon carries momentum given by P equals h divided by lambda. Another important result of the Compton effect is the scattering of photon with a reduced frequency. This important findings of the Compton effect in fact contradicts the classical electromagnetic theory, where in classical electromagnetic theory the change in frequency through scattering is not possible. However, the concept of light quanta or photon permits the change and frequency through scattering. Thus, Compton effect is a more reliable and substantial proof for the concept of particle nature of radiation or for the existence of photons. It further provides the proof that both law of conservation of momentum and law of conservation of energy are applicable in the interaction processes between light and matter. Similarly, the Compton wavelength provides a comparison between the wavelength of a photon and of a particle. To understand this, let's move to the mathematical form lambda c equals h divided by m naught c, where m naught stands for the rest mass of a particle. This equation clearly dictates that the Compton wavelength is an intrinsic quantum mechanical properties of the scattered quantum particles, because it depends only on the mass of the scattered particle, which means for different particles Compton wavelength is different. In other words, Compton wavelength can be used as fingerprints for identifying different scatterers. Moreover, the Compton wavelength of a particle is equal to the wavelength of a photon, whose energy is equal to the rest mass energy of the particle. That is, if the energy of photon equals the rest mass energy of a particle, then the wavelength of the photon equals the Compton wavelength of the particle. This means a diffraction experiment would not be able to distinguish between photons and material particle obeying this condition. The Compton wavelength can be used as a measure of the energy of the scattered particle or electron in the original Compton experiment. Since the particle is initially stationary and the collision is elastic, therefore the energy lost by photon must appear as the kinetic energy of the scattered particle. That is, kinetic energy of the particle equals the difference of the energies of the incident photon and the scattered photon. Substituting the values, this can be expressed as h nu minus h nu prime, or in terms of wavelength, we can express this as hc, the whole multiplied with the difference of the inverse of the two wavelengths, that is 1 over lambda and 1 over lambda prime. And this can be put into a more simplified form by putting the terms inside the bracket into a single denominator, and that can be expressed as hc divided by lambda, the whole multiplied with delta lambda divided by lambda prime. Now, hc divided by lambda in fact equal to the incident photon energy, and delta lambda is equal to lambda c 1 minus cos theta. And from this last equation we can write that lambda prime equals lambda plus lambda c into 1 minus cos theta. Substituting this value back into the equation for the energy of particle, we can write the kinetic energy of particle equals the energy of incident photon times 1 times lambda c into 1 minus cos theta divided by lambda plus lambda c 1 minus cos theta. This equation clearly dictates that the energy of scattered electron is directly proportional to the energy of incident photon. Now, if we keep on decreasing the energy of incident photon, the kinetic energy of scattered electron also decreases with E incident. However, along with the decreasing E incident, the wavelength lambda of the incident photon in the denominator increases. This in turn further quickens the decrease in the energy of scattered electron. Below certain critical energy of the incident photon, all the energy is taken by the scattered electron and nothing is left for the scattered photon. This condition corresponds to the photoelectric effect. The Compton effect can be observed with photons of large energy, that is, with photons in the X-ray and gamma rays regions.